I'm going to go with the spirit of the symposium and talk about disaster mitigation and global climate change. But I'm going to start by talking about where I live. I live in San Francisco. San Francisco is a very nice city, quite beautiful, but it's also a very risky place to live. One of the risks that it's famous for is earthquakes. In 1906, there was a 7.8 magnitude earthquake, and the earthquake, in addition to the fires that followed it, pretty much leveled the entire town, and it had to be built up again from scratch. Now, since then, there have been plenty of earthquakes, there's been plenty of damage, there will continue to be earthquakes, and I, as a good San Franciscan, have learned what to do from the instant I feel the ground shaking, which is to dive for the first piece of furniture I can see. Now, earthquakes are a big problem in San Francisco, but it's not the only problem. Another risk is San Francisco is at sea level, and my house is pretty much at sea level. And as we've heard, sea, and as we all know, sea level is rising. I don't know when it's going to happen, but eventually my house is going to be underwater, and I need to be prepared. And it's not just earthquakes and sea level rise. I just learned this not so long ago. There's a strange fact that in the United States, California, where San Francisco is, has the second highest increase in cases of malaria. Now, some or most, but not all the cases are, of course, people traveling someplace else and bringing it in. But you can never be too careful. Now, it's a good thing for us in this risky city and also the risky world that we as a species have been putting satellites up into orbit for decades now. And we've been hearing from the great space agencies around the world who've been doing this. I am not going to put a satellite slide up on the screen. We all know about many of the satellites that are up in orbit. They're a lot, and the data are hard to manage. If you just look at one Landsat 8 scene, for example, it's 64 million pixels just per one scene. And we're getting hundreds of those every day. The archive has existed for 40 years, it's petabytes worth of data, and that's just Landsat, right? The Sentinel data, satellites are shipping lots of data, all other satellites are shipping lots of data, and it's just getting tough to manage. And until recently, it was also hard to access. For instance, going back to the Landsat catalog, prior to 2008, you had to buy Landsat imagery. The best year that the imagery was available was 2001, available for sale. And in that year, 25,000 of these Landsat images were purchased. Now, around 2008, the US government made the great decision to make the archive freely open and available. And upon making that decision, usage spiked. Just 2 years later, it went up 100-fold from 25,000 to 2.5 million scenes. And since then, it's just skyrocketed. So we've gone from a situation where satellite data were not used that much, they were expensive, hard to get access to, people were working on sort of scene-by-scene basis, to a world where now we have a lot of satellite data, and the problem comes to how do we manage it? If more and more satellite data are made freely open and available, how do we take all that data, work it together, and make it useful? And that's the challenge we face. Is there a way to make all the satellite data that's available accessible in an easy way and analyzable in an easy way to anybody who wants access to it, right? Anybody with access to a web browser. That's the challenge that we faced. Now, there are a few trends in industry that are worth considering when trying to address this challenge. Everything is getting cheaper over time in terms of technology, but things aren't getting cheaper at the same rates. So if you look, these are gross numbers, but the thing that's dropping fastest is the cost of computer processing cycles, followed by the cost of disk storage, and then the thing that's decreasing the most slowly is the price of bandwidth. And if you take these things together, you can drive a couple of conclusions. First, because bandwidth is dropping the slowest, you want to minimize the use of bandwidth. And if you're trying to access lots of data and minimize bandwidth, the best thing to do is get the data next to the processing units that are actually computing the data, so you don't have to move the data around. The other observation is, because this storage is getting cheaper and cheaper over time, you can store much of what you want, if not all of what you want, on disk and make it accessible whenever people want to access it using the internet. You don't have to put it on tape. You don't have to get it off the tape storage when people want it. You don't have to sort of process it over time. You can put all the data up on spinning disk and make it available. And the third observation is, because computer processing units are getting cheaper the most fast, you should try to not necessarily store everything, but try to process it on the fly when you can. So, for instance, if you're calculating a vegetation index globally using 30-meter data, you don't have to store that one pixel up in Antarctica in 1992, because nobody may ever want that pixel. Instead, just generate that on the fly. So this is the approach that we took when we tried to build a system like this. We have, for the last 6 years or so, been downloading as much satellite data as we're allowed to redistribute freely. And we've been putting that information on Google servers and giving programming interfaces out to whoever wants to use them to create their own analyses using that data. There's Landsat data, MODIS data, there's chirps data, lots of different kinds of information, as much as we're allowed to share and that people have demand for. And that's a system called Earth Engine, and it's available at earthengine.google.com. What I'm going to do now is give you some examples of what people have been able to do using this system. The idea is, how do you use all the data, all the data you can get your hands on? The first application I'll tell you is something that we're doing internally. So we've been at Google using geospatial analysis or geospatial platforms for a while. We have Google Maps and Google Earth. And this image was the best image that we had for this part of Borneo in Google Maps and Google Earth. If you went to Google Maps and Google Earth and went to this area, this is what you saw. That was before we had access to the entire Landsat archive. Now that we can look at all 40 years worth of data, we can take advantage of the fact that clouds move. And you can go pixel by pixel and start with the most recent image and go back in time until you find the cloud 3 pixel. You might have to go back 5 years. In some places, you do have to go back 5 years. Those people shake their fists and say, nobody's ever seen our land from space. But if you go back far enough, you can see it. And if you do that, you can clear up the cloudy image. So this is what the image looks like without the clouds. Now, if you use lots of computers, you can take that analysis, which is sort of a pixel by pixel analysis, and you can spread it out over many, many computers using the cloud. And so we did that. We did the same kind of analysis on all of South America. You know, it used to look like that. Now it looks like this. And we did it globally, and that's the currently the base map for Google Earth and Google Maps, the 15-meter global image of the planet as it never looked, right? It's like spring everywhere, and there's not a cloud in the sky anywhere. But it lets you see places that some people have never seen from space. So this is what we're doing internally, but what's most exciting for us is what other people are doing using the system, using cloud computing. And that's what I'm going to spend most of my time talking about. The first application I'll talk about is something from a guy named Randy Sargent, who's at Carnegie Mellon University. He saw what we did here with making a single cloud-free mosaic, and he said, why don't we just do that for every year? So he did. He built something called time-lapse, and it's available at that URL. And this is an image, it's a movie actually, of the entire Earth at 30 meters as it changes from 1984 forward, right? So every place on Earth you can go to and see how it's changed. For example, you can see irrigation in the Saudi desert. You can see rivers meandering over time and cities kind of running away from the river meandering. This is in Peru. You can see cities growing. So here's Shanghai over time. If you look over in the lower left, you can see the land expanding. You can see Las Vegas, which is a huge city, huge growing city in the United States growing. And you can see forest loss happening. Now this was a big analysis. It looked at 29 years of satellite data. It was 2 million Landsat scenes. To create the mosaics, it took 2 million hours of CPU time. If you ran this on one core on your computer under your desk, it would have taken something like 250 years. Right, you'd have to train your descendants to wait for the data until you got it. But because we were able to run it in the cloud and parallelize it and distribute it over 66,000 machines instead of just one, it just took a day and a half to make these mosaics. This is the kind of thing you can do when you have access to this big infrastructure. So this was good for visualization, but I want to talk about some scientific applications. The first one I'll talk about is one that Michael talked about earlier. This is the global forest change. This is a study by Matt Hansen and his lab at University of Maryland. They took the Landsat catalog and mined it for forest pixels and forest change pixels, and created this global map, and they've extended it every year since then. When the paper came out, they launched a site, and you can go to this site and see sort of pixel by pixel, 30-meter pixels, where forest changes happened and when. For example, you can go into Sumatra and see the change happening over time. This is another big study with 1 million CPU hours. It ran over fewer computers, so it took about 4 days to complete. But it's 4 days to complete a global analysis of forest change. And it was good that it took only 4 days because it wasn't exactly perfect the first time, so we had to do some revisions. But because we could spread it out and over lots of machines, it was pretty fast. Now the next step of this is very interesting. This data set was made public and downloadable on the site that I showed you. But another agency, the World Resources Institute, thought that it would design a site around the data and other data sets that would be more designed for decision makers, policy makers, nonprofit organizations, and other advocacy groups. And they created a thing called Global Forest Watch. Global Forest Watch takes that Hansen data, data from lots of other scientists, and combines them into an easy interface. You can go to this location, anybody can go there. You can circle an area you're interested in, and then that call behind the scenes calls the Earth Engine cluster to provide analyses, in this case of how much forest loss and how much forest gain happened in that area. You can also set alerts, so you can circle an area, and whenever forest loss happens in that area, you get an email. Now this is being used all over the place because it's easy to use and it's easy to access. So for instance, in Philippine government and their Congress, they used this site to motivate laws prohibiting the destruction of the mangroves. And just on Friday, a paper was released in Science Advances showing that the international effort to double the wild tiger population, despite the expectations of the researchers, is definitely possible because the forest preserves where a lot of tigers live have actually been protected. The governments are doing a great job of enforcing the protected areas. And in the paper, they talk about how you can use Global Forest Watch to set up a tiger habitat monitoring system. So this is a great example of scientists generating data that's been used by a nonprofit organization to help show the positive effects that governments are having on biodiversity preservation. I'll give you a couple more examples. This is work by the Joint Research Center at of the European Commission on surface water availability. These folks are doing a similar thing that Matt Hansen did with forest loss and gain. They're mining the Landsat archive, going all the way through every pixel they possibly can to identify where water is and where it isn't and how it changes over time. So, water looks, sometimes you can see it and sometimes it's hard to see. So in all these images, there's water, but you can use machine learning techniques. Actually, Matt Hansen used machine learning techniques as well to discover forest, to data mine the archive and find water. And this is what the folks at GRC are doing. They have mined the archive and been able to come up with images that show permanent water and transitive water. And this is another example of a very big run that took a lot of computational power. Another application is agricultural. We have lots of agricultural applications. This is rice paddy monitoring. The authors believe that this is the first 30-meter study of where rice paddies are in South Asia. They did a similar thing. They mined as much data as they possibly can. Now, I really like this study because it has a flowchart. And as a computer science guy, I'm not comfortable unless I give a flowchart in one of my presentations. And the nice thing about this flowchart is it shows all the different data that these folks used to come up with this image of rice paddy farming. Right? They used MODIS land surface temperature. They used Landsat 8. There's some pulsar data in there. There's SRTM, right? Because the data catalog has access to all this different data, they were able to combine it easily because it's all in one place and run this analysis. So now let me talk about some of the things I mentioned at the beginning of the talk. Applications in disaster mitigation. One is earthquakes. I talked about the San Francisco earthquakes. Here's San Francisco. It's a little thumb up there. This is one of the many faults that we're blessed with, the Hayward fault. And this group at Stanford University, David Lamont's group, was able to use USGS models of earthquake damage risk to predict, from a fault line, how much damage could be caused by an earthquake. Now, the earthquake I mentioned happened in 1906, but as we know, there have been earthquakes all over the place, and recently in Nepal there was an earthquake that was of the same magnitude and it caused massive damage. Here's a photo from David Lamont of the monkey temple in Kathmandu. Here's another image of the destruction that earthquake caused. Right after the earthquake hit, this group ran their model and came up with sort of a damage assessment of what the earthquake might have done. This was used immediately by the Nepalese government in their needs assessment. And the reason that they were able to use it was because it came very fast. They didn't have to wait for do a full inventory. They did it later, but at the moment it was the fastest way that they could get the data and incorporate it in their needs assessment. I talked about flood risk due to sea level rise. This is work from NGIS and CRCSI in Australia. They've been building tools on top of this cloud platform to measure the risk of sea level rise. They're using high resolution DEMS and other ancillary data, and with that they're building kind of a dashboard of the amount of damage that sea level rise at different heights can cause. The nice thing about this is it's an application that these folks are building without any involvement from us, and that's how we like it. They know the tools that they want. They can just use our services to build it, and that's what they're doing. A DEM is one way to measure sea level rise. There are other sources of information to do it that you can use to do it. For instance, one is SAR data. SAR data is good at measuring water. We, as soon as we knew we were allowed to, have been collecting Sentinel-1 data. So now we have a whole Sentinel-1 catalog, and we're getting Sentinel-1 data as it comes in. This is kind of a map of the area of Sentinel-1 data that we have with the area. And you can use that to do some flood mapping. So, recently, around November in Chennai, there was a lot of flooding. You can look at the Sentinel-1 data from before the flood, so this is like November 12th. You can compare it to the Sentinel-1 data that came about 10 days later or 12 days later, and do a simple difference and see where water is now that wasn't before the flood. The Pakistani government used a system, it was more sophisticated than the simple difference system, when their own when flooding happened in their country. The Sacred Suparko program used Landsat 8 data and Sentinel-1 data in this platform to assess the damage that flooding in the areas caused. And the last thing I talked about in my risks of San Francisco was malaria risk, right? There's work out of the University of California, San Francisco to help measure the risk of malaria. What they're doing is they're taking, this is Swaziland, where the pilot is happening. They're taking data recorded by doctors in the field. They're combining it with elevation data, satellite data. So this is a wetness index derived from Landsat. And they're combining all of these data to develop malaria risk maps. Now, you can predict where the mosquito that carries malaria is going to break out based on environmental data. Also, you can measure risk based on roads data, closeness to hospitals and things like that. And you can, over time, make these risk maps. You can look to see where the risk is highest and most stable. So that's this area. And then you can compare it to where mosquito bed nets have been distributed. And you'll see that there's some lack of overlap between where the nets were distributed in black and where the high-risk areas are in red. Those are the remaining areas. Then you can sort of zoom in into the area and see whether it's a habited area or not. And if it is inhabited, you can distribute mosquito nets there. So this is a project that they're piloting now for use of resource allocation to help mitigate the risk of malaria. I'm going to leave it there for the examples and just summarize the conclusion. The main point of all this is that we're living in interesting times. The advent of cloud computing, the advances in machine learning and artificial intelligence that are happening are really revolutionizing the kinds of analyses that you can do with remote sensor data. And the ability to sort of bring all the data you can get together in one place and do the analysis is really making it possible to leverage the full set of data that we have available. You'll notice that all of the examples I gave relied on people who are not us. Google, we're good at building tools. That's what we love to do. But we don't know the science. We don't know what is going to be successful outreach to people who can make decisions. We build systems that other people can build upon, and that's what we like doing. And that's why it's so exciting to be here and why I'm so honored, because really, we all need to be working together. We need to be taking all of the data that we have available, combining it in a way backed by the best science that we're all building, and we need to be able to put it into the hands of people who know how to build interfaces that can be used to turn the data into information. And by doing that, by combining all of our efforts and all our talents, we can help really address the challenges that are facing our species, facing ourselves, and facing our families. Thanks very much.